All right, so in today's class, we're talking about water treatment, um, all the different sort of methods that are mechanical and chemical. And then our next class, we'll look at sort of more biological. We touch on it just briefly, but so you definitely need uh, clean water if you're using pond water and also if you're using recirculating water. Um, Rainwater typically is stored in a cistern and as a result can stay fairly clean, but it's not uncommon to get contaminants in a cistern, so there's still going to be some filtration. But 99% of greenhouses recirculate their water, so they have to have some form of filtration. And one of the reasons, well, sometimes if you're treating well water, you can have things like sodium levels that are too high. Um, you're definitely dealing with potential pathogens in your water that you need to eliminate. Uh, you know, the Ministry of the Environment has very strict rules around nutrient runoff from farms. So that's a real reason for why we don't discharge into the environment to begin with. So that means that we're doing a lot of treating of water. So, and then sometimes it's just simply adjusting the incoming water, like your well is really alkaline, or if you have rainwater, the pH is, depending on where you're at, very, not quite ideal for your irrigation purposes. But so there's a bunch of reasons, but the main one we're focusing on today is going to be particles, which I should really put here is debris, right? Debris, stuff, peat moss, perlite, roots, biological flakes, bits of bran and vermiculite. Everything that you've seen at the college is at greenhouses as well. So, um, from a biological perspective, the key fungal and bacterial infections. Well, I'm going to go over them all, but this is a fungal one, Rhizoctinia. This is one that tends to rear its ugly head more in the summer when plants are a little more susceptible because of the higher heat. But typically, you get a black stem around just around the soil level, and then eventually it will sort of almost damp off, and then the plant chokes off its vasculature, and the plant wilts and dies very quickly. Uh, it's often misdiagnosed, but rhizoctinia is fairly common. Um, in fact, rhizoctinia attacks a lot of grass outdoors if it's a particularly challenging summer. So, anyways, rhizoctinia, the spores get in the water and they spread, and infected plants can actually infect a lot of other plants very quickly if that water passes through the root zone and is recirculated and sent on to other crops. So, really gotta sterilize the water to prevent that. Pythium, you've all heard this before. This is, basically everything from down below the soil level starts to rot. And the classic symptom is where you can slide the roots off the steel. That tells you have a Pythium infection. And the roots usually are very weak or, non-existent almost. So Pythium is another bad one for recirculating water. Phytophthora is another one. This one uh, does not have this part here. It's not filamentous, so you don't see any sort of fuzz on the structures. This is what it looks like in a tomato. This is what it looks like when it's infected an apical meristem and it's moved into these petioles. Um, it's not so much in the roots per se. It's more in the stems and upper plant structures. It does move through the veins, and it happily moves through your irrigation water. So that's another one that we want to treat. And yeah, you're looking at standing water is definitely not a good thing. So make sure that you keep your, any leaks in the greenhouse are fixed so that there's no constant supply in an area of water because you'll generate Phytophthora spores. Fusarium is another one, otherwise known as vascular wilt. Uh, it does not present as a black stem. That's how you would differentiate Fusarium from Rhizoctinia. And looking at a cross section, the pith has sort of an orangey brown color as opposed to a healthy one. That's your first indication. This is a tomato vine that's been cut with a sharp knife lengthwise, and you can see the brown central cambium. And these are the conidia. They look like little bananas that float around in the water, and they get into irrigation water, and they spread big time. A lot of these fungal issues are more of a problem in the hotter weather in the summer, but you can see them any time of the year. But either way, we treat the water year round to make sure that we don't get fusarium. And fusarium will also infect fruits. This isn't on a tomato, obviously. So it's not just in the vasculature, but it will, if it's left untreated for a long time, it just it just goes from bad to worse. Bacterial leaf spot, otherwise known as xanthomonas. Sometimes this is fungal, but a lot of the times when you see these sorts of spots, it's bacterial. And it's mostly to do with overhead irrigation. And if you continue to overhead irrigate and water splashes off a spore area onto a new leaf, it will spread. So it's really important to contain it. And if you do have it, discard the plants that are infected and or change your irrigation practices. A lot of times farms, when they see this, they spray with a copper-based insecticide because that will suppress the bacteria. It's fairly effective, but when you're selling ornamentals, this is not nice to look at, so it's not popular. But we do get in the veggie industry as well with tomatoes, and that's where we see them mostly, where we see bacterial leaf spot. But it's everywhere. Even in Niagara, walking around in the summer, you'll see it on peach trees and plums. And yeah, so clean water. Lastly, I believe this is my last one, there is Erwinia. I don't know if you guys have heard of this one. It often affects succulents. This is a picture of an orchid, but I've seen it in cacti and in the aloe plants and stuff like that. But any succulents they seem to be quite prone to Erwinia, but it can be in other stems. It's just maybe a little easier to see in succulents. But you get kind of a glassy, soft, you can see that here, this sort of glassy edge between a normal leaf and the bad section. And again, they move to the vasculature, so they'll spread throughout the plant. And of course, if you get water bouncing off this onto neighboring plants, it spreads. So clean water is absolutely essential. So what are the basic stages of water treatment? So in a greenhouse, typically we have a coarse pre-filter, and this is what removes big objects from returning water after irrigation, things like soil and perlite and vermiculite and care tags and yeah, whatever. Then we move on to fine filters. And then lastly, we have a biocidal stage where the water is disinfected. So we're going to go through the different types of equipment and their pros and cons. So yeah, coarse filter removes large debris, anything greater than 1 millimeter. Typically, this is a larger volume of waste in this area. So it's got either a higher throughput or a larger surface area to deal with all the debris. When it comes to fine particles, less than 1 millimeter, sometimes all the way down to 10 or even 5 microns, these are what we call our final filters. And these are ones that we put in place to make sure that drippers don't plug, that kind of thing. But they do not stop bacteria and spores and viruses from passing through. Then there's the biocidal stage, which is where we kill bacteria, fungi, spores, and sometimes viruses, but not always. Okay, so the disinfection stage. We're going to look at a lot of these today, and there's a lot. Greenhouses spend a lot of time and energy on clean water because that is critical for safe, efficient production of crops. Because if you end up spreading disease throughout your entire crop, your losses can be massive. Bacterial canker, another good example. Clean water is really important. So, So there's things like pasteurization. That's how our milk is treated at the grocery store. UV, bromine, sand filters, slow sand filters. We're going to go through this whole long list. Um, but before we do that, I want to list off some things that you should consider. So these are important questions I put on quizzes and midterms. So how effective is it, right? Are there limitations? You should always know. You know, do you need redundancies? What is it capable of? What's it not capable of? How long is it active? This relates to sort of sterilizing procedures and how quickly they react. So we'll talk a little bit about that. But for example, UV light can shine through the water and will, destroy living organisms, even viruses, as they pass through the water. But the flow of the water through the UV light impacts how long the water is exposed to the UV light. And so you need to know if your exposure time is long enough to kill everything that you need killed. And more often than not, that is not the case. So you have to be really careful. That would be just one example. How expensive is it to operate? What are the costs? Is it electricity? Does it have chemicals? Is there media that you have to constantly replace? What is the maintenance and labor? What's that going to cost you to operate the system? So those are other important considerations. And lastly, how adaptable is it to load? This sort of relates back to the contact time, because depending on the time of the year, your biological load can be high or low. Typically in the winter, biological load is lower, and in the summer it's higher, especially if you have an outdoor irrigation pond. And so then we have to make sure that when we have flow rates, that our system is capable of handling that load. So that goes back, like I said, to longevity of the sterilizing action. So in these cases, a chemical you add to the water that stays in the water is going to continue to act on sterilizing the water as it flows through the pipes, not one specific locale where it has contact and then it's gone. All right, coarse filters. Let's talk a little bit about that. These are to remove large contaminants. So the common ones are sand media filters. This is sort of what you see in a pool. Disc filters, cascading screens, and cascading screens with paper media. We'll go through them all, and I'll tell you right now that this one here is probably one of the most common in the ornamental world. And I think I've seen it in a number of commercial veggie houses as well. Note, as I go through these slides, up here in the top corner is sort of help you to give a clue as to where we are in the different types of filters. Because some of these filters, like, for example, they qualify as both a coarse and a fine filter. And some are only a fine filter, and some are only a coarse filter. So just be aware of that nomenclature as I'm going through the slides. So, a sand filter. This is your standard pool filter, if you've ever seen one. They operate on the same principle. In a greenhouse, they're typically a little larger, and they're made of steel, and they look kind of more industrial. But the principle is exactly the same. The idea is that when you're in the filtering process, water comes in and is pushed through the sand. It migrates through the sand to the bottom and then goes into collector tubes, which you can see over here, and then goes back up the center and comes out filtered, clean. Now, when you want to, when the filter starts to plug up from debris and your outflow rate starts to diminish, you're getting very slow output, you backwash the filter. And what that really means essentially is all you do is reverse the flow. So you come down the center, out the bottom collectors, and through the sand, and up and out, and divert this to waste, to your septic system or whatever. And as you reverse the flow, the sand all lifts in suspension. Typically, you don't lose much because it's too heavy to fall out of the filter. They're designed. The vertical height is such that, the sand will agitate, but not exit necessarily out the backwash. but the debris, all the stuff that was filtered out, will actually make its way out. And so you get a flush of dirty water. And so typically there's a sight glass, and you backflow the water until the water coming out is clean. And then you stop it and you reverse it to normal filtration direction. There's another on the right. This is a commercial greenhouse configuration. These are the sand filters, and these are the various valves for whether you're backwashing, or you're actually filtering. So, and then here's a pool system showing you how it works. And normally this is all full of 2/3 full of sand. I just made a real mess of it. So yeah, you fill the thing up to about this crease here, all full of sand, and that's your filter media. And sand will last for quite a long time. So what are the pros? It scales to different flow rates. Typically sand filters can, if they're sized, they can go to just about any flow rate you want. So that's very helpful. I know for our hydroponic lettuce, we use sand filters for our primary filtration, and then we used ozone for sterilizing. But yeah, we use sand filters very successfully. They are fairly low maintenance except for backwashing, and a lot of backwashing is actually automatic. There's a switch that senses when the pressure drops, and then it automatically closes the valves, reverses, and sends the water backwards for a predetermined amount of time. And then it automatically switches back to filtering, and it will just maintain itself. So you just have to keep an eye on it. Whoops. They usually do not affect the chemistry of the water. It's really important to get the right kind of sand. Should be like a granite-based sand. If you get a limestone-based sand, it's going to make the pH really high. So you got to be careful. Not to mention your fertilizer solution will actually dissolve it. So within a few weeks, your sand is actually gone. As far as pros, the sand filters is very effective all the way down to 5 microns, depending on the media you use. Sand is not usually all the way down to 5 microns. Sand can go down to 10 or 20. But 5 microns, on the next slide I have a picture to show you, but diatomaceous earth works really well, and that will filter out bacteria, but nothing will filter viruses out. They're just too small. We make it through. Negatives, yeah, maybe they take up a fair amount of space, but really it's not that bad. You need to replace the sand every 3 to 5 years. I mean, again, not a major big deal. It's just sand. But probably the biggest one is the backwash. Now, the Ministry of the Environment knows that these filters backwash, and they want to know what you're doing with that backwash. So it has to go into some sort of either a truck, right? Truck it away, and or it goes into a certified treatment facility. That could be a septic bed if it's sized accordingly, or it could be into a artificial wetland. We'll talk about that next class. There are some options, but just be aware that they're going to be very, very interested in what you're doing with your backwash. Diatomaceous earth is actually, these are tiny little algae that are predominant in the ocean. They're in freshwater too, but there's a lot of them in the ocean. And they show up as sort of chalk deposits because diatomaceous is actually chalk. They press it into a cylinder and that's your chalk. They put it as a powder into your toothpaste and that's the abrasive, because these shells, which are made of silica, they're beautiful glass-like structures, and they all the different species of algae have different shapes, and of course, as they deteriorate, they break. And those glass shards, when these are all broken into sharp pieces, that's what this whole pile of white stuff is. It's basically glass shards. Now they're so small, it's not like they're gonna, cut your stomach or something. But diatomaceous earth is also used as a organic insecticide, because this dust, if you dust it on the ground and insects walk over it, they get it on their joints, and the glass shards actually abrade and scratch the joints to the point where the insect's exoskeleton breaks open, and then they dry out and die. So it's not a toxic way to kill bugs. It's actually very safe. If you have pets, this is a great way to control insects is by using diatomaceous earth, because if they eat it, it's not gonna hurt them. Um, Diatomaceous earth is used in all kinds of things. It's used as thickening agents in paint, in resins, all sorts of stuff. It's a big industry. Um, it is mined from the ground, like ancient seashores that are below the surface. That's where we get a lot of our diatomaceous earth. I believe Turkey has some very big deposits, but they're all over the place. South America's got a bunch of mines. But these are beautiful under microscopes. What you're looking at here, these are scanning electron microscopes of diatoms. So, anyways, I've probably spent more time than necessary talking about that. Um, the next type of coarse filter is what's known as a disc filter. These filters are more common, I would say, in large nurseries because they can position them out in the field. They don't take a lot of space, and they actually automatically backwash. Now, it's very difficult for me to describe verbally how these work. Um, I'll try, but you should know this video link works. My video file was getting big for this lesson, so I decided not to include a video of this because you can go back to your PowerPoint, click on this, and you can watch the video. But what it is the water comes in on the outside of these, like on the outside, it comes in here and goes around the outside, and it squeezes through a stack of plastic discs. So these are hundreds of plastic discs that are stacked together. There's a mild amount of pressure put on them, and the discs have kind of a rough surface. So you can imagine that the water has to kind of squeeze through each of those plates. So here's your water's coming in. It has to squeeze through the plates to get to the center and then exit out the filtered end. And of course, debris, will start to get caught in between the discs and plug them up. And eventually the water doesn't flow so well through the discs. So what the system does is it actually reverses the flow. So the water comes in. Let me get my blue color. So the water comes in this way instead and shoots into the center and then shoots out the other way and knocks the debris out, and it goes through the entrance and then diverted into waste. So there's backwash. And of course, what's especially cool about this is that the discs actually move apart when you reverse the flow. They open up and loosen, so the debris comes off very easily. And then when you reverse the flow back to normal again, everything snaps shut, the discs all slam together again, and it starts to filter again. So it's pretty slick setup. I did have one of these in my greenhouse for my ornamental greenhouse for filtering stuff so hanging basket drippers wouldn't plug. But I see these a lot more in nurseries because they have fields way out. It's not necessarily a greenhouse. You're driving on a tractor way out in the field, and they run the irrigation pipes underground. Then they come up to different sections where they have risers, and then that's usually where they put these filters. So anyways, watch the video to help you explain what they do. Now, they're simple to operate. They have no media to replace. Like, they basically last a very, very long time. They can handle quite a high volume of throughput. And especially when they're automatically backwashing, they're very low maintenance. One of the cons is, of course, that it's a backwash, right? So what are you going to do with it? Same thing as with the sand filters. These typically go down to 50 microns, and the really coarse ones to 200. So you're definitely not catching, all your pathogens, but you get a lot of debris, but you won't get a lot of bacteria, and you'll get some spores, but I would not consider this bactericidal. I would consider this a fine filter for making sure your drippers don't plug. But it definitely needs to be paired with a biocidal step if you have problems like that. These you've seen lots of times around the greenhouse, these screen filters. I'm not going to get into how they work. You've seen that before. You open up this cartridge, and inside is the screen filter. They're a bit of a pain to clean because they don't automatically backwash. You have to take the cartridge out, soak it, scrub it, put it back in again. But they don't alter the chemistry, but they definitely do not filter pathogens. And you should know that the different colors actually mean something. So we have a lot of yellow ones at the college, but we do have some black ones. And look at the dimensions. The black ones have much larger pore sizes, so they're less likely to plug up, but they let more debris through. Depending on your drippers, you might get some plugging, but usually we go with yellow, the yellow ones. But yeah, mostly we have yellow and black at the college. So they go down to 75 microns, but these plug very quickly. A lot of the times in greenhouses, these small filters are just an added insurance step. So for example, if you have you've got, say, your main filtration in the barn and water's going out to the greenhouse to maybe your irrigation boom. Typically they'll throw a couple of screen filters on the actual irrigation boom just because you don't really want that machine to get plugged because it's hard to work on and it's critical. So it's easier to just to clean a little screen filter periodically to make sure your boom is operating properly, rather than having to pull nozzles and put new nozzles on, and it's just a real pain in the butt. Micron filters, you know what? Honestly, you don't see these very often because these cartridges are expensive. You know, you might have one in your house, which you have to replace every, maybe 2, 3, 4 months. They're definitely effective, but they're expensive and you can't reuse them. So that's an ongoing cost. Typically, this is like a large capacity, these tanks. You just unscrew them and slide a new filter in. But honestly, I don't think I've ever really seen one being used commercially in a greenhouse. They definitely are, they can't backwash. You have to have a pretty clean source so they plug up instantaneously. So really not sure, but I put it there because I have seen it at cannabis facilities. But maybe if you have city water coming in, I could say if you're not recirculating, then it could work. Your city water is pretty clean. But really you should be recirculating your water to prevent loss. So I would say it's not very common. These are very common and they're pretty cool. It's called a cascading screen filter, and I've got a video coming up with a similar filter that will help explain this. But essentially what happens is, so actually if you look here, there's sand filters. Interesting, eh? So they're actually after the cascade filter. So the main water that comes back from the crops is pumped up to the top of this, and the water runs down like a waterfall into this box, and then it's collected and pumped through the sand filters and sent out to the greenhouse. Now the way this works is this, you can't see this angled, this sloped surface is a stainless steel screen that has hundreds of thousands of holes in it. And what actually happens is as the water runs down, the water falls through the holes and lands on the other side of a box. It leaks through the screen and comes out the back side. So I kind of misled you there when I first described it. And all the debris, the perlite and the peat moss and the care tags, they slide down the front and they end up in the front bucket. This part here. And that's how it mechanically separates debris from the water. So it's called a cascade filter because the water cascades down over a porous surface, and the debris that doesn't fit through the pores ends up in the front, skimmed off. These are very effective. There's no consumables. There's very little maintenance. They remove all the stuff to get your water ready to go into your next stage of filtration, so you don't overload your sand filters too quickly. Especially in an ornamental greenhouse, there's a lot of perlite and stuff. These are very helpful. Which, there's a picture of an outdoor water reservoir. This has got a cover on it. So typically a lot of greenhouses use these. And the outdoor water is being pumped up and cascaded down, and you can see all the debris that's accumulating. And the water falls through the back and then goes back into the tank. And this is actually just falling on the ground, which is kind of messy. But, whatever. So that's a cascade filter. Now, a cascade filter in combination with a media filter is really popular in greenhouses, and they work really well with recirculating systems. They don't alter the chemistry. They catch all the coarse stuff, They do not filter pathogens, and they do go through cellulose rolls, which are expensive, but you don't go through that much, so it's worth the expense. And the main thing is that they're just really darn effective. Um, Essentially, what it is a cascade filter, like I just described, right? So there's your slope back, and then what's rolling over top of that filter is a paper media. So it comes off a roll, slides down the front, and comes up and out the other side. And that's what you're seeing in this picture. You're seeing the dirty paper that has come from the other side of the cascade. And as the water runs down into this hollow area, it percolates through to the bottom and gets filtered. And the debris, which collects on the paper, is slowly removed as the paper is rolled through the filter at a slow pace. I've got a video coming up that's going to help explain this. But so the pros, works great, doesn't alter chemistry, you know, and it's pretty reliable. So here you can see the water is coming in, and it's got lots of sand, and the sand is getting caught on the paper. The way it works is that this probe right here, this probe, when the water starts to back up into this valley and gets high, it touches the probe, and then it triggers these wheels to rotate, and they pull fresh paper down into the valley. And so the dirty paper comes out the other side and is collected as waste. So these are very popular primary filters. And you can see here the water is cascading down. The waste paper is actually going directly into a bin, and when the bin is full, they cut it off, roll it out to a dumpster, and throw it away. And it's just biodegradable paper. It's, you know, not a big deal. And it's very clean and effective at removing large debris. Here you can see there's another roll ready to go. Fine filtration. So let's look at some fine, these are sort of the finer steps. That's 5 to 50 microns. Not a lot of farms do super fine filtration. It's not really that critical, but some they do need to. Maybe propagators where they're using high pressure fog and the nozzles plug easily. But so one of the more environmentally sustainable ways is what's called a slow sand filter, and the other one is a micron cartridge, right? So we already saw those, and we know that those cartridge filters are expensive. A slow sand filter is not a pressurized one where you reverse the flow like our other sand filters. What it is an emphasis on large, a large container. In this case, it's underground, right? In this particular farm, they've got pre-filters, settling tanks, and then they pump it into the sand filter where it percolates down through and goes into the pond. And that's how they're removing particles. The idea is that you have a large surface area so the water slowly percolates through the sand. And the sand will, you know, catch the debris. But because you don't backwash it, what actually happens is you get biological activity right at the interface where all the particles are. And that biological activity will eat it up and break it down. And what's really interesting about this is the process of breaking it down also disinfects. So not to the point that, you know, it's sterile, but to the point where there are definitely some pathogens that are eliminated. So that's pretty cool. There's actually organizations that sell slow sand filters to third world countries to help treat drinking water ecologically. Pretty cool. So they're low maintenance once they're built. They don't have a lot of electrical demand because the water moves through passively for the most part. And if you have your properties on a grade downhill, it's even better. But you still have to pump your water back up to the top to use it at the farm. But you can definitely percolate the water through the entire system very slowly. Like I said, they don't eliminate all pathogens. Some, we're going to talk more about this next class when you get into biological filters. Cons, they can be very big, you know, large tanks, large surface area. And a big con for in Canada is that they don't necessarily work well in the winter because they freeze, right? So not many, like that other one was below the ground, so there's some ground temperature. So maybe in Niagara, there's some times when it might actually work. But you definitely have reduced biological activity in the winter. So something to be mindful of. Okay, so once we've done our coarse filtration and our fine filtration, we move on to biocidal strategies, right? So biocidal is any process or substance that is lethal to a living or reproductive biological organism or product, like a spore. So bacteria, spore, viruses, not always viruses, but we hope we can get them, but they often get away from us. Um, Typically, they are oxidizers, right? So I've got a slide coming up that compares different oxidizing levels, but other than heat pasteurization, which is one method, well, we're going to cover them all, but they're generally oxidizers. And the strength of the oxidizer dictates how fast and complete it is at sterilizing. So chlorine is kind of a benchmark for the industry. So there's your bleach. It's kind of weird talking about this in light of COVID because, you know, everywhere we go, we're surrounded by this kind of stuff. I think it's our new reality for a while. Anyways, oxidizers are potent. I don't know if you can remember the scene. This is from the Breaking Bad. Do you remember the bathtub scene? Anyways, oxidizers, yeah, they burn through a lot of stuff. And this is the symbol, this flaming O for oxidizers because they burn and they can burn your skin. So this is kind of a this is I guess this is one chart that's used to kind of compare oxidative capabilities. I'm going to focus on this one. So they compare them to chlorine as the standard. So bromine is less oxidative than chlorine. Then you get into things like hydrogen peroxide, which is pretty good. Ozone, very good. And then of course fluorine, which is, you know, really, really strong oxidizer. So uh, typically in greenhouses, hydrogen peroxide, if you're adding chemicals, or bromine are used. Chlorine is not so typical. Um, we're going to go down through this list, but I don't want to, you know, this is just summarizing all the different things that exist. Let's start with pasteurization before we get into all the oxidizing ones. Now, there are some big farms that actually still use pasteurization. Uh, Pasteurization actually will knock back viruses, which is, you know, I guess you can consider pretty helpful. But it's expensive because basically you have a dedicated boiler that has to heat all the returning irrigation water up to 80 degrees Celsius, and it has to stay there for a minimum of 20 to 30 seconds. Typically, they hold it for longer than that. Commercially, milk is all pasteurized. They heat it, same thing. They have high temperature heat exchangers with hot water from a boiler, and the milk passes through it. And the milk is heated up to 80 for a short time, and that kills not all the bacteria. You know, they have only about 5 to 10 second exposure time, but it kills 95% of the bacteria, which means that your milk will last longer in the fridge because you've got fewer bacteria starting with as they start to grow again slowly in the fridge. That buys you time. That's why milk has an expiration date, because the bacteria will begin to reproduce slowly in your fridge and get to a point where if you drink it, you'll get sick. So pasteurization is just to make it safe, you know, mainly going after E. coli and salmonella. But so what are the pros? Well, it's very, very effective against bacteria. Even nematodes, which are fairly large organisms, can be difficult to kill with some oxidizing agents because they're big, complex organisms. But here, viruses. So you can imagine veggie farms, there some of them might still do this because of the very fact that viruses are impacted. Now UV lights will also kill viruses provided your flow rate is not too fast. We'll talk about that later. Here's a veggie farm. This is all the big tanks that store the various irrigations when they come back. So you might have different feeds, sunny, cloudy day. or freshwater reserve. There's usually about 6 of these things. They're big, put it in perspective. That's a forklift there. And they're very wide. Anyways, they take that water and they'll heat it with a boiler and hold it at more than 80 degrees Celsius for a while. And then they put it in another tank, let it cool for a day. And then they take the tank that's cool and that's what they use for irrigation for that day. So it's always rotating through the various tanks. This is an interesting thing. It's a single point, no residual control. That means that the water is only treated where it gets heated to 80 degrees Celsius, as opposed to adding a chemical that is persistent in the water as it moves through the entire irrigation system. It has a lasting residual action. Pasteurization does not have that, so that's a downside. Obviously, it uses energy. That's not good. That's going to cost you, money. So it is considered old school, but like I said, quite a few farms still use it, and I think it's primarily for the viruses component. Looking at UV is where basically you've got a waterproof quartz tubes that have UV lamps in them, and water is passed around the tubes where they're exposed to the UV light, and then they exit. Now, UV light is bactericidal because as UV light shines through the water, it shines through the bacteria and the viruses and the spores, right passing through their relatively thin cell wall to the inside of the organism. And UV light actually breaks DNA and protein and mRNA. It breaks it apart. And it takes too much for the organism to repair those breaks, so the organism dies. So it's like shooting a shotgun through the bacteria as they shoot through the water going through the irrigation line. Now the question is, if they're shooting really fast, there's a possibility that they manage to escape being hit by the UV light, or they don't get enough of a dose. Maybe it only breaks a small piece of DNA and it's able to fix it and survive. So the flow rate is really important for the effectiveness of UV sterilizing system. Another one, and this is one that concerns me with greenhouses, is that these quartz glass tubes, they have to be quartz because normal glass absorbs UV, right? We want the UV to penetrate through the quartz into the water, so we have to use quartz. But anyways, the water that's coming back leaves residue on the quartz. And it's like, say this is my quartz tube. Over time, you get a film of minerals and whatnot that form around the quartz, and the UV, which used to be, really strong, ends up becoming kind of weak because a lot of it can't penetrate through that film. And so you have to take them apart and you have to clean the tubes at least once a year to make sure that they're actually doing anything. There's lots of people that have UV filters in their homes and they probably never opened them and they have no clue really if the UV is even doing anything, just using electricity. There's no chemicals, which also means there's no residual, right? You only have contact when the UV light is shining on the water. Once the water exits that tube, there's no more biocidal activity. So all the biocidal action happens while the water's in that short tube. So your flow rate is really, really critical. So you need sufficient contact time to sterilize, right? So that's a really important one for UV light. Now, I'll talk about bromination, but before I do that, we'll talk about chlorine because obviously, kind of, if you're thinking about pools and hot tubs, chlorine and bromine are used, right? We've all swam in a pool and smelled like chlorine. Pool water is not very good for plants, and the main reason being is that they cannot control how much they take up, and it will reach toxic levels in the plant and kill the plant. Whereas bromine is a little safer. The plants don't take it up as readily. So you can treat the water and it will stay in the water, but you don't want any more than 35 ppm parts per million bromine in your irrigation water. So growers that use bromine have to do water tests daily to make sure that there's nothing wrong. Because if you go above that, you could kill all the plants in your greenhouse. So that's just another job for the grower to check on their daily routine. Um, Bromine is definitely effective, though. It has a residual activity, which is great. That means that you add it at a point. This is what a bromine doser looks. It goes out into the greenhouse, and it is continually sterilizing the water as long as there's biological activity until it's all used up. Uh, it does require monitoring, right? We talked about that, testing daily. You have to buy bromine pucks constantly. Typically, these last anywhere from 6 months to a year, depending on how much you're using. And you're looking at maybe $300-400 to fill it with pucks again for the subsequent year. Um, if there's a lot of biological load, so you're pulling from a really scummy pond, it may not be effective at sterilizing the water completely. It's not a very strong oxidizer. Remember from my chart, it's 0.7 of chlorine, right? It's on the bottom end of oxidizers. It's, not that strong at killing stuff. So, moving on to ozone. Ozone is a very effective sterilizer. I use this in our lettuce at our greenhouse. Um, this is actually similar to one we had. This is a generator in here that produces ozone, and it bubbles it through the water, so the gas is injected, and the water and with the gas injected goes through a contact tank. This tank, the water slowly moves up through the tank and then moves out to go into your greenhouse for irrigation. And the gas that's collected at the top accumulates at a little charcoal filter. So the bubbles will sort of rise, and as it fills, it burps out excess gas. Now, that's a really important part because ozone is dangerous for plants, and we want to make sure the ozone is dissolved in the water and not released in the greenhouse as a gas. So the system has to be working properly so you don't get ozone in your greenhouse. But typically it is set up so that basically you generate ozone using electrolysis and oxygen. You bubble air through your water and you apply a high voltage, and the oxygen, instead of being O2, will recombine to O3, which is ozone, right? And you do that using adding electrons with these high charge plates and bubbling air through the water. And the ozone, which is fairly water soluble, it actually reacts not just with living organisms, but biological material like biofilm. And as it reacts, it breaks it up into smaller pieces, which then flush away and clean and are caught in your filter. So ozone is really effective. Um, in cannabis facilities, they even use ozone in the air to destroy odor. So if you have, smelly stuff coming out your greenhouse that goes through here, they add in ozone by using charged plates, and it takes the regular oxygen, makes ozone, which breaks up all the terpenes and whatnot that are stinky, and come out the other end as smaller molecules that don't smell. So it's not just for treating water, it's also an odor treater. It's even used to remediate homes that have mildew problems. So if there's mildew in the house, they will run an ozone generator. Obviously, you shouldn't be in there because the ozone will damage your lungs. But the ozone then penetrates the rugs and sterilizes them and breaks up the mildew spores and everything and sterilizes it. So um, it's cheap to operate. All you need is a little bit of electricity, not a lot. It's very effective at killing bacteria and spores, but not viruses too, actually. But it depends on whether it's a DNA virus or an RNA virus. But the RNA ones are a little more susceptible. The DNA ones sometimes are a bit too robust, but it does kill a lot of them. There is only a little bit of residual activity, not as much as bromine, for example. But probably one of the biggest disadvantages with ozone is it reacts with iron in your water. So typically you have to add extra. You need extra iron in your nutrient solution if you're using ozone because it will react and precipitate it out. And then also, if it escapes as a gas, it can damage your crops. If you see a lot of really white specks like this, that is actually ozone damage. So now typically you would see it closer to the barn where you have the machine, not on the far end of the greenhouse. Then it's maybe something else, thrip damage or something. But if you don't see evidence of, bug poop or eggs or nests, and you see all these white spots, think ozone. If you're using ozone to treat your crop. There's actually some crops like tobacco plants, Nicotiana, they are very sensitive to ozone. And sometimes like ornamental tobaccos, if you grow them in the city, they actually get spots on their leaves because of low level ozone pollution, which of course is made by UV light from the sun reacting from our emissions from our vehicles. Hydrogen peroxide. This is a very effective one. All you do is inject it into your water, and it sterilizes the water, and it has some residual activity. So, relative to chlorine, it's a 1.8. So it's almost double the oxidative value. No, sorry, yeah, chlorine down here is 1.4. This is the volts, but it's about 50% stronger than chlorine proper. Anyways, hydrogen peroxide is a liquid that you inject into the water. Uh, it is effective against bacteria, spores, and viruses. Uh, you have to be careful that you don't overdose because it will actually burn roots. So that's just operator maintenance. There's usually what we call the dissolved oxygen meter that you can use or a DO meter that will tell you the oxygen level in the water and the ozone. So you check that regularly to make sure your machine's not overdosing your peroxide. Um, so those are kits that are available. But anyways, it has residual activity. This is the nice thing. So you inject it, it goes out. Not only does it kill the bacteria in the water as it's flowing through your irrigation lines, but it will also remove biofilm from the pipes and the drippers and keep them clean. Like, for example, if you look at our hydroponic rockwool blocks at the greenhouse, they have some algae on the top from nutrient solution being exposed to sunlight at the top of the block, and there's maybe some green on the drippers. If you run peroxide in a system, that actually kills all that algae and keeps everything clean. So, uh, we don't do it at the college because we don't really have any major problems, but our problems maybe our problems are more major than that. That might be more of a case. But anyways, it's something we probably could do, but we don't really bother. Obviously, you have to buy the hydrogen peroxide, so that's going to cost you some input money. It's not super cheap. I think hydrogen peroxide, you probably are looking at about a commercial, like an industrial barrel size for a 1 acre farm every month. So figure how many acres, multiply that barrel. That's quite a bit. Barrel's about $150. So that's not cheap to operate. The other thing is some plants are sensitive. That's more in the ornamental world. But I haven't actually seen many plants that are too sensitive. Some lettuce varieties, but generally speaking, pretty safe. It just like ozone, hydrogen peroxide reduces iron because it's an oxidizing agent, and a fairly strong one at that. So you have to increase your iron content. Another system that is good at sterilizing water, and this is more popular in the ornamental world, and this is really only the last 5 years that people have started installing these. But essentially, it's like a saltwater pool chlorine generator, and they're actually called electrochemically activated water, or ECA water. And what you do is you put in potassium chloride. So in this tank here is potassium chloride. You just dump a bunch in, add some water, so you have a thick concentrated slurry. And then what happens is the system will suck a small amount of potassium chloride in, inject it into the water, and then pass the water over some electrical plates, just like the ozone generator system. And it reacts with the potassium and the chloride to make oxidizing agents that then flow out into the water and have a residual sterilizing activity. So ECA is pretty cool. It's actually been used by janitorial companies for quite a long time. they would have an ECA machine in a cabinet, and they would use it to fill their mop bucket or something like that. Um, and that way they're not always adding chemicals, and that mopping water will then sterilize the floor and whatnot. But it's effective at killing bacteria, spores, and viruses. Um, and the real bonus here is that, of course, you're also adding potassium. So not only that, but you're also adding a nutrient, right? You're adding potassium to your crop. So that's a bonus. Um, as far as ECA is concerned, it's not a very potent oxidizer. It's slightly better than chlorine, though. So not bad. Not bad, really. So here, there's a video explaining this process. Again, if you go back to your PowerPoint slides, you can watch that video. Uh, Basically, I'll review it. You take your potassium chloride, you expose it to electricity, and it takes the chlorine from the chloride. So your potassium chloride has chlorine and potassium. And the chlorine is converted into chlorine gas. So these bubbles then dissolve, react with water, and form hydrochlorous acid, HClO, or hypochlorous acid, sorry. And that hypochlorous acid is what does a lot of the sterilizing in the water, killing bacteria and viruses. And then you say, well, what about the potassium? Well, the potassium goes through the same electrochemical process and is converted into potassium hydroxide, which is a lot like Drano, right? And what do we use Drano for? For cleaning pipes. So the potassium hydroxide actually removes biofilm and cleans irrigation lines. So it's a double whammy. Not only is it sterilizing, but it also cleans your irrigation lines. So, and you get the bonus of the potassium once it's done reacting, that is potentially in your soil as a nutrient. So it's not wasted. This is my attempt at describing with diagram how this works. So you have a plus and a minus, like an anode and a cathode, and the potassium chloride dissociates, goes to the respective charged plate, and then reacts with the water to form chlorine gas and potassium hydroxide. All right. So typically it's safe. I haven't seen any plants that have been damaged by it. There's no dangerous chemicals to store. Potassium chloride is not toxic. It's not going to melt your arm. It's perfectly safe. I wouldn't run around drinking it, but it's just salt. It's what we use to clear snow in the winter because potassium chloride is cheaper than sodium chloride. There's no dangerous chemicals, right? Like I just said, there is no residual from the process that's really dangerous. The hypochlorous acid it reacts with the water and cleans it and evaporates, just dissipates. It's not a big deal. Fairly inexpensive to buy potassium chloride, like I said. So, what are the cons? Well, you need to monitor your chlorine levels. If something goes wrong and it has too high a chlorine level, then you could maybe start damaging your crops. Because remember, right at the beginning, I said chlorine, plants can't control how much they take up. So if your system goes out of whack, you might damage your crops and you might have too high a chlorine level. And then you'll burn your crops. So, but other than that, there's really not a lot of problems. ECA is pretty popular. I know right on the corner from me is a big orchid grower, and they put in ECA about 6 years ago, and they love it. A lot of ornamental growers use it. Copper silver ionization. This is an interesting one. I only know of one ornamental grower that uses it. I think there are more, but I don't know where they are. Essentially what happens here is you take a piece of copper and you apply electricity to it. You notice that electricity is used in all these things. These are all electrochemical reactions. And I should explain that the reason being is that when you're dealing with oxidative agents, we're dealing about electrons. So electricity supplies the electrons that allows us to make these things. But essentially with copper and silver, what happens is by applying electricity to this, the atoms come off the plate and go into solution. This is kind of how you copper plate something, right? So you apply a voltage to the copper and then you ground the object that you want to copper plate, and the copper ions will move from the copper over onto the whatever object you want to copper plate. But in the case of the greenhouse, there's copper plates inside this device, and you apply some electricity, and it puts copper ions in the water. And copper, along with silver, is bactericidal and virucidal. Now, if any of you buy Norwex cloths and stuff like that, you've probably heard of that, especially because of COVID. Norwex has fine silver threads that are woven through the fabric. So a small percentage of the fibers are silver. And of course, as you use the cloth, the silver comes out into solution, and the silver is bacterial cidal. So that's how they help stay clean. But yeah, copper and silver are bactericidal nutrients. Um, Very effective as at killing pathogens, and they do also clean up irrigation lines. This is a commercial greenhouse showing here you got 1, 2, 3, 4, 5, maybe more of these cells producing copper ions into the water. But some downsides. There are some crops that are definitely phytotoxic. Remember, copper or any metal, even iron, is a micronutrient. Now, it's not one that is that important to plants, so we don't add it to our nutrient solutions. But because it's a metal, it can substitute for other metals. And the plant can take it up to cytotoxic levels where you end up with micronutrient toxicity. So you've got to be very careful that you don't overdo this and damage your crop. The other problem is that if water is exiting your farm, let's say you're backwashing a filter or you just drain out the water from your farm, copper is considered a pollutant. It's a metal pollutant that will contaminate your land. That can cause you some serious problems. So you got to be very careful about what you do if you're using copper or silver to sterilize your water. Now, biofilters and using more organic approaches, we're going to discuss that in the next class. Um, so I don't know why I just drew that. It was just meandering. But I think that's an interesting topic I want to put into another lesson, not cram this one full. We've already got 57 slides. So, all right. I hope you found that interesting. I can tell you a lot of greenhouse growers, they love their boilers and they love their water systems. They're big parts of their farms. So, all right. I'll see you next time. Bye.